house for all involved, I'm sure.
Yeah, pretty much.
So what do you got for me?
Okay, so I have my final review, and I really need to work on verifying.
Trig identities?
Yes.
Okay, do you got some?
Uh-huh. Hold on just 1 second. So I have, let's see, secant squared x over cosecant squared x. And that's it.
Okay. What's the reciprocal? In other words, usually when you're trying to simplify stuff, if you can't see anything else, in other words, I do know that secant squared is tangent squared plus 1. Okay. But that's making 2 terms out of it instead of 1. So that's probably not the direction that I want to go.
Right.
However, it's also what? What's the reciprocal? Those are the ones that are most important in solving these.
1 over cosine.
And since we're switching that one into cosine, let's switch this one into sine.
Okay.
And now do that division by flipping and multiplying. What's that equal to?
Oh, tangent squared x.
Yeah. So usually the name of the game here is to reduce it, to take 2 terms and turn it into 1 term.
Okay.
It's usually not correct to go the other way. In other words, like I said, I could have turned that into tangent squared plus 1, but that's taking 1 term and turning it into 2 terms.
Right.
So, okay, what else?
All right. I have 1 plus secant x over secant x equals sine squared x over 1 minus cosine x.
Okay. Well, let me think for a moment. Usually when we have part of the equations in sine and cosine, it makes sense to put everything in sine and cosine.
Right.
So I can switch these to cosecant, cosine.
Right.
And then at least I will have everything in sine and cosine. And it should be obvious as to which way to go after we do that. So if we say the numerator is 1 over cosine x, and the denominator is 1 over cosine x, now let's act on the numerator by finding what? How do we add these 2 things together? Find a common denominator. Always find a common denominator. Okay, well, the left side has to be cosine x. The right side has to be cosine squared x.
Okay.
Is this, and the key is that the same exact thing as that numerator? In other words, this numerator here. It's not.
No.
I did it wrong. It's cosine x is definitely the denominator, but this numerator over here is just 1. Okay? Now I can see that I've done it correctly.
Okay.
In other words, I didn't change it. Okay, and I'm dividing by 1 over cosine x, so I'm going to multiply over cosine x over 1, which simplifies it greatly. So now we have cosine x plus 1, and somehow that is to equal this. Well, cosine x plus 1 equals sine squared. It's not against the rules to fiddle with both sides?
She usually says just do one side.
Okay, I agree totally with her, but sometimes you can discern stuff by figuring with the right side. In other words, we're not going to fool with it, but it may give us a clue. Right? So far, so good? That difference of perfect squares? So that becomes 1 minus cosine x times 1 plus cosine x. Now we can see that they are identities.
Okay.
So the secret now, since you're only allowed to operate on one side, let's multiply top and bottom by 1 minus cosine x. So here's what I'm going to do to the left side. Cosine x plus 1, I'm allowed to multiply that by the number 1. And the number 1 I'm going to use is 1 minus cosine x divided by 1 minus cosine x. Okay? Well, that's the difference of squares factored. Right. So that turns into 1 minus cosine squared x over 1 minus cosine x. And now I can substitute sine squared for that, and voila, there's my right side. Okay. So the lesson to be learned here is that you can gain insight from fiddling with the right side. Remember one thing about trig identities. They do not exist in nature. Right. You will never find an engineering problem or anything else that requires you to verify trig identities. They are for one purpose and one purpose only, and that is to teach the student their identities. Because usually after you spend an hour or two working with verifying trig identities, you know your 11 primary identities very well. It is great practice for learning your 11, in other words, your 6 reciprocal, your 3 Pythagorean, and your 2 quotient identities. But turning this into what we were looking at wasn't so easy without playing a little bit with the right side and realizing, well, at some point I had that. Well, I know how to turn that into that. Right. And so coming up with this step, and let me say one other thing. When you're doing trig identities, whenever you see this, whenever you see this, and in our case, whenever we saw this, or this, well, those in themselves are difficult to turn into simpler identities. Right. So the one thing, the one trick of verifying trig identities is to usually multiply these by their conjugate. Not just their conjugate, but their conjugate over the conjugate. In other words, I can always multiply that by 1 without changing its value. And the advantage of that is it turns the numerator always into something that you can then replace by 1 term. In other words, now I can replace that with sine squared x. And so I've taken 2 terms and eventually squeezed it down to 1 term in the numerator. Now, it's true that I've made 2 terms in the denominator, but sometimes that's just what you have to do. And the key is to recognize this. Whenever you see a 1 minus or a 1 plus, know that if you multiply that by its conjugate, it will turn into 1 term.
Right.
It will either turn into sine squared or cosine squared. So a lot of times that's what you want to do.
Okay.
And there's not much else you can do with that. There's no other identities for these. And it's similar to if you see secant squared minus secant squared minus 1 is equal to what?
Is that tangent?
Yeah, tan squared. Okay.
Mm-hmm.
So if I were to come across something like secant minus 1,
Mm-hmm.
well, I would immediately think of multiplying that by its conjugate.
Right.
Or even secant plus 1 and multiply it by its conjugate. Either one turns into that,
Mm-hmm.
which turns into that. So keep your eye out for things like that and what I had on the previous page.
Okay.
It's not always correct to multiply by its conjugate, but frequently it is, which is kind of strange because, like I said, these were created by somebody to teach you your 11 primary trig identities, and that's a bit of an algebra trick right there.
Yeah.
In other words, multiplying that by the conjugate produces difference of squares, produces an identity.
Okay.
So that's just something you kind of have to remember when you're working with verifying trig identities.
Okay.
Got another one?
Yeah. I have simplify tangent pi over 3 plus tangent pi over 6. And then that's all over 1 minus tangent pi over 3. And then tangent pi over 6.
Times tangent pi over 6?
Yeah. Mm-hmm.
What does that look like?
Oh, wait, the bottom one is times tangent pi over 6. Not 3.
Yeah.
For the second one, yeah.
Sorry. What identity does this remind you of?
The one with secant.
No, it's the tangent of sum and difference.
Okay.
Okay? In other words, it's apparently that they're going to test you not just on your 11 primary trig identities, but they're going to test you on sum and difference also.
Okay.
This looks like tangent of A plus or minus B.
Okay.
And the reason I say that is tangent of A plus or minus B is tangent of A plus or minus B divided by 1 minus or plus tan of A times tan of B.
Okay.
Well, that's exactly what we're looking at there. A and B are pi over 3 plus and pi over 6.
Okay.
So what we're looking at, we can immediately say that that is the tangent of pi over 3 plus, not minus, pi over 6.
Okay.
And they want a number for this? Or do they want an expression? Is this multiple choice? In other words,
It's multiple choice.
Well, pi over 3 plus pi over 6 is what? 2 pi over 6 plus 1 pi over 6, that's pi over 2. And tangent of pi over 2 is undefined.
Yeah, that's one of my choices.
That's the int.
Okay.
Okay. In other words, you didn't actually have to go in and solve this. You could have by solving all of this, but what's apparent to me is that that number right there is going to be 1.
Right.
Then you're going to have 0 in the denominator, and division by 0 is what gives you undefined. So, but knowing your sum and difference identity makes this easier, because you can immediately say that they're talking about the tangent of pi over 2, and if you're really familiar with your trig functions, the graphs of them, you know that tangent is undefined at minus pi over 2 and plus pi over 2 and any multiple of pi after that.
Okay, so I'm confused how you got pi over 2 from pi over 3 and then pi over 6.
Unless I made a mistake. I hope not. Let's see.
No, you didn't.
Well, I might have. That's 2 pi over 6 plus pi over 6. That's 3 pi over 6, which is pi over 2.
Okay, that makes sense.
Okay. But the biggest thing I noticed was then when you were giving me this answer, it fit the sum and difference identity perfectly that I knew.
Right.
And I mean perfectly. I didn't have to fiddle with it at all. This is definitely A, that's definitely B, that's A, that's B. And the signs fit. Notice that you do need a plus sign in the numerator and an opposite sign in the denominator.
Yeah, I think she'll always do that because we just started learning like those.
Okay.
Yeah.
So what is this one? Without looking at your book. And that's the way to do these.
Okay.
In other words, when you're trying to memorize trig stuff, you don't want to have a list of them in front of you, not unless you're going to be allowed that on the test.
Right.
Are you, or do you have to have all these memorized?
I'm pretty sure she'll give us all of those, but I don't know about the trig identities.
The first 11?
Right. She'll give us like cosine A plus B and then the formula to get it, but I don't think she'll give us
what
the
verifying. The reciprocal of yeah. The verifying stuff is usually based only on the first 11 identities. So you definitely want to have those memorized. Whereas these, one easy way to memorize these is they each have cosine, and 2 cosines and 2 sines. And this always starts out with the 2 cosines. And then the sine is opposite of what this is. And the last 2 have to be sine, since I know there's 2 sines and 2 cosines. And then to memorize sine, well, it's really easy, because I know there's still 2 sines and cosines, but it's sine, cosine, same, sine, cosine. Now, where do my letters go? This is A, this is B, this must clearly be B, and that has to be A. In other words, the second part's always going to be the opposite of that. They're never going to repeat it.
Right.
Okay. So that's one way to memorize those 2. And the tangent is just kind of easy to remember if you, I don't know, I had a hard time remembering the tangent, but notice the tangent, the numerator is exactly the same, and the denominator is one opposite, meaning minus or plus, and then the product of them. Tan A, tan B. Okay, so when you gave me something that looked like this, which you did, I immediately thought that's the sum and difference of tangent.
Right.
And it's much easier to calculate what this is by using that identity, although I guess you wouldn't have to. You could always just, is this a calculator problem or not?
No.
Well, even without being a calculator problem, you can figure out that the tangent of pi over 3 times the tangent of pi over 6 must be 1, even if you use your two basic triangles.
Okay.
And the fact that this product is 1 subtracted from 1 gives you a denominator of 0. That's all you need.
Okay, yeah, that makes sense.
The denominator is 0. Your answer is undefined regardless of what the numerator is. So as long as you knew how to do that, you didn't really need to do the easier route, which is that one.
Okay.
Have you had beyond sum and difference? Have you had half angle and double angle?
Yep. We've done all of those. But I think she'll give us a list of all those formulas.
So you don't need to memorize those. Okay.
No.
Okay.
I have, let's see. It says solve and then find all solutions of
Go ahead.
4 sine squared x equals 1.
Okay. Obviously, just like any algebraic equation, we want to come down to sine x equals something.
Right.
So how do I get to that step?
So divide by 4 both sides.
Okay.
And then take the square root of both sides.
So sine of x equals what?
Square root of, well...
What's the square root of 1/4?
1/8.
This is a hard concept for most people to get. When you take the square root of a number smaller than 1, it gets bigger. It doesn't get smaller.
Okay.
It's not like taking the square root of numbers bigger than 1.
Okay.
If I take the square root of 4, it gets smaller. It becomes 2. But if I take the square root of 1/4, it becomes 1/2.
Okay.
Why? Because 1/2 times 1/2 is equal to 1/4. But
yeah, that makes sense.
Any time you take a root, square root, cube root, any root of a number smaller than 1, it's going to get bigger. The key here, though, is that in addition, whenever you solve any equation by taking the square root of both sides, begin your answer with plus or minus, always.
Okay.
Because minus 1/2 times minus 1/2 is equal to 1/4.
Okay.
So both of these are equally valid. And now, what's x equal to? Where did they give you a domain x between 0
and
pi?
0 and 2 pi.
So where in your unit circle is sine of x equal to either plus or minus 1/2? Let's start with the first quadrant.
30.
Second quadrant.
Let's see, 60. Well, 150.
Third quadrant.
210.
And fourth quadrant.
That would be 330.
Okay. Now, the fact that they gave you the domain in radians, does that mean they want the answer in radians?
Yes.
Are these all going to be multiple choice?
I don't think this one is.
Okay. How many
yeah, this one's not.
Well, how many radians is 30 degrees?
Pi over 6.
How many radians would 150 degrees be?
5 pi over 6.
Right, it's 5 times that, right? 150 is 5 times 30, therefore it has to be 5 times this.
Okay.
And this one?
7 pi over 6.
And this one.
11 pi over 6?
Yeah, the way I think of this one is that's a pi over 6 short of 2 pi.
Okay.
Right? In other words, 360 degrees would be 2 pi. This is 30 degrees less than that. So it's got to be 2 pi minus a pi over 6.
Okay.
I mean, there's all kinds of methods you can use to convert these to these. You can just use the straight conversion, pi over 180. But after working with it for a lot of years, I kind of like the method of knowing the following. Know that 30 degrees is pi over 6. Know that 45 degrees is pi over 4. And know that 60 degrees is pi over 3. And that times that's 180. That times that's 180. That times that's 180. So if you make this identity early in Trig, then it helps you figure out, well, what's 150 degrees going to be? Well, it's 5 times that. It must be 5 pi over 6.
Right.
And to me, I have found that useful to do it like that. But you do have to remember those first 3 first quadrant conversions. If you can remember those, then figuring out the rest is relatively easy.
Okay.
This plus or minus is important. If I would have only come up with a plus, then I would have only had that solution and that solution.
Right.
I would have missed these two here, because those are negative. And I guarantee you, well, I'll bet you this was one of your multiple choices. Or you said this was not a multiple choice.
No.
But if I was giving a test and I was making a multiple choice, I would have given 30 and 150 as one possibility, and then all 4 of them as another.
Yeah.
Just to catch the people that miss the plus or minus.
Right.
All right. Today is one of my busier days of the year. I am stacked up straight through.
Okay.
So I don't mind being just a minute or two late. Do you have one more you want to do real quick?
Yeah, I'll do an easy one. Evaluate the sine, and then in parentheses, tangent, inverse tangent, root 3 over 2.
Always work from the inside out. Where is the tangent equal to root 3 over 2?
That's the tangent?
It's a weird one, isn't it?
Yeah. So 60?
No?
No.
Nope. Nowhere. Hold on. There must be a spot, but it's not the standard triangle. You sure that it was inverse tangent of root 3 over 2? Really?
I have the answer.
What is the answer?
Root 21 over 7.
Okay, I get it now. Here, I was fooled by that common thing there. If I want theta, which is what we're solving for when we look at inverse tangent.
Oh, do you have to make a triangle?
I have to make a triangle, and that's theta. Okay? And tangent of theta would be root 3 over 2. Now I have to fully dimension the triangle. Well, it's 4 plus 3. It's square root of 7. So now, what is the sine of theta? In other words, I don't know what theta is yet, but I know what the triangle is.
Yeah, right.
So the triangle is root 3 over root 7. And that reduces, if I rationalize the denominator by multiplying top and bottom by root 7, I get root 21 over 7.
Right.
So, yeah, I got fooled by the common ratio right there, thinking that that had to be one of the 30, 45, or 60 degree angles.
Yeah.
This is a very common solution where you draw a triangle and you try to dimension it.
Yeah.
All right. Emma, you got another one scheduled this week, I think?
Yeah, tomorrow.
Tomorrow, I will talk to you then.
Perfect. Thank you.
All right, bye-bye.
Bye.